My name is Hanson Smith, and this is my video abstract where I'm going to be talking a little bit about the what and why of my paper on the non-monogeneity of division fields of elliptic curves. Okay, so first off, what's monogeneity? So a number field, k over q, we say this number field is monogenic if the ring of integers of k is generated by alpha. Looks like z-adjoined alpha for some algebraic integer alpha. Okay, so that's monogeneity. And the first friends you meet when you're learning algebraic number theory are all monogenic. So for quadratic fields, the ring of integers looks like z-adjoined the square root of d or z-adjoined 1 plus the square root of d over 2, depending, of course, on what d is congruent to modulo 4. Okay, and then the next friend you make along the way is the nth cyclotomic fields, and these are monogenic. They're generated over the integers by an nth root of unity. And I want to pause right here to give a little bit about the why of why I would study the division fields of elliptic curves. A somewhat fancy and geometric way to think of these number fields is these are the GM division fields, the nth GM torsion field, and they're monogenic. So the multiplicative group of Q is a nice group, and if I adjoin torsion points of that group, I get monogenic number fields. So a natural question, I think at least, to ask is, what about other groups? What happens if I adjoin torsion points of other groups? Is there something about torsion and monogeneity? What's the relation here? So that's the why of why I would start asking the questions that led to this paper. All right, and not every number field is monogenic. Dedekind was the first one to come up with an example of a non-monogenic number field. And he looked at the field generated by a root of this polynomial right here. He computed that 2 factored into 3 primes, 3 distinct primes in this field. And then another theorem of Dedekind, often called Dedekind-Kummer factorization, shows that if 2 doesn't divide this index right here, the index of a monogenic order generated by alpha in the ring of integers, then the factorization of the minimal polynomial of alpha, mod 2 in f2 adjoined x, mirrors the factorization of 2 in the ring of integers. So we're looking for a cubic polynomial that generates our number field and that factors into 3 distinct linear factors in f2 adjoined x. Now this is one of those things, if you sit and think about for a minute or two, you realize we can't find such a cubic polynomial because there are only 2 linear polynomials in f2 adjoined x. So this number field can't be monogenic. And even more than that, 2 is going to divide the index of any monogenic order in the maximal order. So in this case, we say 2 is a common index divisor. And you also hear essential discriminant divisor and inessential discriminant divisor in the literature. And I think those two somewhat contradictory terms for the same thing are coming from the difficulty of translating the original German phrase for this phenomenon. But we call it a common index divisor to avoid confusion. Okay, cool. So we got common index divisors, and we're asking the question about whether or not monogeneity is this phenomenon you always get with torsion, with adjoining torsion points, whether division fields of elliptic curves are monogenic. And the short answer here is no. There are a lot of division fields that are not monogenic. So this is the short punchline here. And if you want to see the gory details, which actually aren't that gory, and a worked example, you can look at my paper. But if you want the rough, quick definition of what's going on in this theorem, if you give me an elliptic curve and you give me information about the endomorphism ring of that elliptic curve over Fp, then we can compute the n for which P is a common index divisor in the n division field. And so here's a table where we've done this for P equals 2. Here's the trace of Frobenius, and this is a lovely matrix we get from a nice result of Duke and Toth. And if you're interested in an open problem here, we have how to get the spacing of this matrix in this cell to be nice. For some reason it's nice here, but it bumps up. Anyway, that is not the point of this abstract. So a second kind of look at or a second kind of way of playing this main result. And this is a different theorem, but it's another way of seeing that there are a lot of these in-division fields for an elliptic curve that are not monogenic. And that's if you give me an elliptic curve without complex multiplication over the rationals, then there are going to be infinitely many n for which the in-division field is not monogenic. And to be specific, if I get a large enough supersingular prime, then the p+1 division field will have p as a common index divisor. Okay, cool. So that's some theorems telling us that this phenomenon of monogeneity is something special about the cyclotomics that we don't always get for free with division fields. But when do we get it for free? Or not for free, but when do we get it? And what causes us to get it? So here's kind of a tantalizing monogenic family that leads us in some directions for what the relation between monogeneity and the arithmetic and geometry of these groups is. In this case, the group being the group of points of an elliptic curve. So if I want to put my elliptic curve in Legendre form, it requires solving the sextic right here, where J is going to be the J invariant of my elliptic curve. And so the theorem is if the sextic is irreducible, then J is divisible by a high power of 2. And both of these quantities, J over 256 and 1/64 times J minus 1728 are square free, then the 2 division field is monogenic over Q with actually this lambda, this x coordinate of a 2 torsion point, generating a power integral basis for the ring of integers. And what's really interesting here that I want to point out is that what we're really asking is that, or another way of putting this is, if I have primes for which my J invariant is congruent to 0 or 1728 modulo p squared, those primes are obstructions to monogeneity. So I think this is really interesting, this kind of like lifting, when I have elliptic curves with more automorphisms that lift, that seems to be blocking monogeneity. And I'm really interested in figuring out more precisely what's going on here. So yeah, if you have any questions, obviously feel free to look at my paper or shoot me an email. So thank you for listening to my video abstract, and yeah.